Hi everyone, today I'm going to talk about the theory and product design for entanglement-assisted communication. And this is work in collaboration with Zhezhen and Saika and Bulat. So you are probably familiar with these scenarios, but just briefly flash the scenarios we are talking about. So we consider the communication where we want to send either classical or quantum communication. And in the unassisted case, there's no pre-shared entanglement. You just encode your information onto some quantum state and send it over the channel. And then on the other side, you will decode to get information. On the other hand, if you have entanglement assistance, this means that there's some entanglement pre-shared to the receiver side by some ideal channel. And then you still encode on the signal part and send over the channel, but decoding can also be on the entanglement assistance and the signal. And one thing I do want to point out is that besides the formal formulation by Burnett Shores and others, and the super dense coding, which Justin already talked about, here the information can be both quantum and classical in this assisted communication scenario, because if you assume unlimited entanglement, then 1 qubit is basically equivalent to 2 classical bits by unit protocols of super dense coding and teleportation. So if you have 1 EBIT established, 1 qubit transmitted, you can just do super dense coding because of you have entanglement, then you achieve 2 classical bits. And if you have 2 classical bits, then you have unlimited entanglement. Unlimited entanglement, you can do teleportation to do 1 qubit communication. So all the results talked about here apply to both quantum and classical information transmissions. Just to refresh, what is the entanglement-assisted capacity of quantum channels? It's by this famous paper in 2002, 20 years ago. So it's very nice in the sense that this formula has a mutual information form, which is the analog to Shanno's capacity formula. We know the high-level capacity, Schumacher-Smeltland capacity does not have this nice quantum mutual information form, but in this case, we can restore this form. So this picture is this unitary extension of the quantum channel. This is the input to the channel. This is the output of the channel. And this is the entanglement assistance R. And this is the purification output of the entanglement extension, of the unitary extension. So the capacity formula is given by the mutual measurement between R and Q here. And you can also express it by the this equivalent formula. So in 1997, very interestingly, even before this 2002 paper, Adami Serve, they showed that they defined this so-called phenomenon capacity, which is exactly the same thing. And they show that it's additive and the concavity, even before the capacity is formulated. So the first thing we worked on is to generalize this capacity to multiple access channels. So multiple access channel means that instead of having a single sender, a single receiver, you have multiple senders sending inputs, and then this multiple access channel will combine these inputs to the receiver side. And the receiver still, because it's entanglement assisted, still have access to the entanglement ancilla of all these senders, this pairwise entanglement. And the capacity has is the regularized region of this one-shot, one-state region of also a mutual information form, but it's now conditional mutual information where J is any set of users. And to better understand this formula, you can consider a 2 user case. Then, for example, if you choose J equals both users, 1 and 2, this means that it's the mutual information between the entanglement assistance of user 1, user 2, and the received signal state. And you can choose J equals 1, so it's the single sender formula, and then this is A1 and conditional A2, and this is A2 conditional A1. And these 3 formulas together will decide the one-shot, one-state capacity region, and in general, you have to regularize. It is still an open question whether you can just get rid of this regularization, prove additivity, and this is ongoing research. I just also want to point out that 2 user cases also before our result is given by shared Debbie Winker, but our result generalized this to arbitrary senders. just to give some examples. So now let's consider, instead of general channels, we consider bosonic channels of thermal loss. And so this thermal loss channel can be described by this Heisenberg-Bogolubov transform of the input AS mode, and you mix it with the thermal noise mode, and you get the output mode. Experimentally, this is just a beam splitter and insertion, a lot of noise in the system, MB, and then there's just a finite transmissivity between 0 and 1. So it turns out that for the single extender, single receiver case, the entanglement-assisted communication capacity is analytically solvable and maximized by the input of squeezed vacuum state, two-mode squeezed vacuum state, which Zheng was referring to in his talk. And in the Burnett paper in 2002, actually it was already known that the ratio of this entanglement-assisted capacity over the classical capacity can go to very large number when the number is small, and here is the plot. However, the practical protocol achieving these advantages is not known. So super dense coding fails with noise. So Zheng has mentioned about this qubit-based super dense coding. You can also consider the continuous variable-based super dense coding, and it still fails because of the noise, and it doesn't achieve anything more than 2. And the reason is that in the bosonic case, it's a single mode, so there's a very large Hilbert space you can make use of it. So if you truncate the Hilbert space to qubit and then use it, it's not the good way to use it. And for the super dense coding, it's more technical why it fails. You can refer to that paper. So first, because we know the in principle input state of two-mode squeezed vacuum is the optimum. However, the general way of achieving the capacity would require some not very realistic way of modulation on this input state. So that will have to be the, for example, either position-based encoding, decoding. Then you would need a large block to actually realize it. And also, if there were other proposals like the original capacity achieving proof, you have to use these Paulis, and you have to convert these qubit Paulis to the continuous variable case, which is not very clear how that is done. So instead, we actually consider this phase modulation. So just explain in detail what is phase modulation. It basically, if you think about the mode as a complex number, it shifts the phase of the complex number by theta. And what we showed is that if you calculate this set of state generated by two-mode squeezed vacuum and the phase encoding at the receiver side, the whole level capacity of this ensemble, the whole level accessible information about this received state at the receiver side is equal to the entanglement-assisted communication capacity of this thermal loss channel plus a correction that is decaying with the input thermal noise. So when the thermal noise is very large, this is the asymptotic optimum encoding. And you can verify numerically by just looking at the plot, either continuous phase encoding or even binary phase shift keying will be able to saturate this capacity advantage when the noise is large. Here, noise is about 20 for the number, and the NS is very small. And kappa is like 0.1. These numbers are not very important as long as this noise is large. And these are the protocol designs. However, here we use the whole level accessible information. So it assumes the optimum receiver, which in general is hard. So we also want to think about what are the practical receivers. And Zheng has intuitively introduced the phase conjugate receiver. And here is the theoretical formulation of how this receiver works. It's by an optical parametric amplifier that basically performs a two-mode squeezing operation, and then by tuning this gain to be 2 or even smaller, you can have the phase conjugated receive signal part here, and then you do a 50-50 mixing with the idler modes, then you do photon detection, and then do the photon number difference. This is basically a way to transmit the correlation in the modes on the quadrators to the photon number difference. And similarly, you can also just use an optical parametric amplifier to do the same conversion. And these two receivers actually originally designed by Guha and Erkman in quantum illumination, while here we use it for communication. And we calculate the capacity, compare the rate achievable by these receivers, assuming the ideal case, comparing it with the classical capacity. And to be experimentally realistic, one thing is that we have to do repetition of a large number of modes to actually achieve a appreciable information rate, so that good encoding and good codes actually exist, and the error probability is not too bad. So this repetition, as the repetition increases, the rate will decrease, but in some limit of 10 to the 8 number of repetitions in these parameters of, I forgot to put parameters, but it's a small meaningful number, so the number of repetition allowed is very large. And the advantage, theoretical advantage, is shown to be about 20%, and in the Zhenzi experiment, it was achieved almost 18%, and it's pretty appreciable. And a slightly better rate can be achieved by this so-called sum flux generation receiver, which I don't want to get the detail of. You can refer to this theory paper, which is originally for quantum elimination, and then this theory paper explains how it can be used here. It achieves a factor of 2 advantage in presence of this large noise and loss. It's similar, looks like similar to the super dense coding, but actually the mechanism is very different. And the super dense coding does not work. The rate will be about here in this such large noise. It will be below the classical capacity in this case. And yeah, as Justin mentioned, there's this experimental demonstration, and there's towards the optimal receiver, you can refer to Sakaguha's next talk. So let us also consider the case of multiple access channels. So here it's a model of multiple access channels in the Bosonic domain. So you have the same thermal loss channel, but the input is by a beam splitter array, or so-called linear optics transforms on these input modes. So these modes are combined and mixed on this beam splitter array to produce these mixture modes, and then this mixture mode is sent over the same thermal loss channel. And the senders can share entanglement, but in this case, the entanglement is pairwise. So each sender has the entanglement with the receiver in an independent fashion. Multiple type entanglement is not allowed in this multiple access channel scenario. Well, one can think about whether that is something worth considering, but for now, it's independent entanglement between each sender receiver. Considering this two-mode squeeze vacuum as the inputs, although it's not known to be optimum or not yet, it's a still open question what is the optimal input. We can still achieve appreciable rate advantage over the classical rate region. So this is the trade-off of user 1's rate over the coherent state rate, user 2's rate over the coherent state. And in general, it will be a trade-off. And these cyan curves are the entanglement rate region offered by two-mode squeeze vacuum, while these pink ones are the outer bound. And this classical region is on this left bottom corner, which means that the entanglement assistance gives a much better rate region trade-off than the classical ones, relatively. And this is the coherent rate region, and this is the outer bound of classical. So nothing can do better than these dashed lines. So the advantage is appreciable here. And we also see that in this large noise limit, it looks like the rate between different senders are almost independent. And this is actually also true for even for the classical case because of the noise. And you can also evaluate this for multiple users, like this 3-user case where you have this outer bound and achieve region, classical outer bound and the classical coherent state region. And you can obtain, you can still show that appreciable advantage can be observed. And we can generalize those receivers, including optical parametric amplifier receivers and these phase conjugate receivers into either the parallel fashion or the serial fashion. So in a serial fashion, the same OPA on the return signal and the first user's entanglement ancilla will first do a gain, which is close to 1, and then produce the same photon, the first photon counting result on the Euler beam, while the signal can be further used onto the second receiver, onto the decoding the second user's information, and this is the entanglement assistance of the second user. And you can show that because this gain is very small, this output of the return signal is almost unchanged in this case, and you can actually rigorously calculate how the results are correlated. You can compute the general joint distribution and then evaluate the rate formula. And similarly, for all the other cases, you can do the same. And this is the practical receiver's performance in terms of communication rate in the two-sender case. These different colors are different receivers. So there were 4 receivers and these 4 colors. We can see that the best ones are the phase conjugate receivers, although they all look very close to each other. And we see they can offer some amount of less than a factor of 2 advantage over the classical coherent state region, coherent state region. However, it is not known in the classical case which input state is the optimum. Actually, squeeze a little bit can actually do a little bit better. So, but still, these practical receivers can still beat the classical outer bound, which is the upper limit on how classical rate can do. So this corner part is the rigorous advantage, while this part of advantage is against the practical protocol. And before I closed, also we want to address maybe some more practical imperfections. For example, phase noise. So as we know in a communication scenario, it is very hard to do this so-called phase locking or establish a phase reference. This will require very non-trivial feedback control and in the long distance. So can we do something again about this phase noise? So this paper is a recent one that analyzes the effects of this phase noise, assuming that you can have some stable phase within a block of M modes. So this is practical because even for very turbulent channels, there's still a finite correlation time, and within that time, there are still some modes that have the same phase, although we don't know exactly the overall phases, but this modes will have the same phase. And this model is also utilized in earlier work about classical capacity. So you can model this as a channel like that. So first you have a phase noise channel which applies the same phase rotation on M modes together, and then afterwards these modes go through the thermal loss channel, and then you can decode on the this side. You can write it in also just like a photon number measurement. So because we know phase rotation is generated by the photon number, so actually if you have phase rotation across these multiple modes, it's equivalent to measuring the total photon number across these M modes, small M modes. And you can write down these projectors. It's a projection onto the fixed total photon number subspace, and then you can write out this formula. So the overall channel can be decomposed as a multi-mode thermal loss channel. Either before or after it, you have a general overall phase rotation that is unknown to you. So you can show that in the pure dephasing case, when the transmittivity is 1 and there's no noise, then even though this is a non-Gaussian channel because you have this non-Gaussian photon number projection operators here, even though it's a non-Gaussian channel, the quantum capacity and the entanglement-assisted capacity can be exactly solvable. And this is by observing that the complemental channel is actually just obtaining these total photon number counts, and it is the entanglement breaking. Therefore, the channel, because the channel where the complement is entanglement breaking is Hadamard, so the all capacities trade-offs are additive. So it will be actually interesting to see whether the trade-off regions can be exactly solved in this case. And also we showed that
we are out of the regular time. I just wanted to notify you because I tend to write chat messages, but maybe if you don't see them, you don't get my warnings.
Oh, so the time is up, or?
Yeah, we wanted to leave 10 minutes for
okay.
Q&A. In case there are no questions, of course, then you can finish the talk. But maybe we should first ask people that have a question to raise their hand.
So yeah, there were 3 slides left. Maybe just show briefly, then
okay.
we can.
I also don't see people raising hands, so then yeah, please just continue.
Okay, so I will just brief in the last few slides. So the capacities can be exactly solved, and the input states actually optimum is non-Gaussian state, and then you can compute these capacities, and the advantage can be obtained either considering non-Gaussian input or entanglement assistance. And in this case, it's interesting that the non-Gaussian input states, because it's a non-Gaussian channel, so you would expect the non-Gaussian state to actually do better. And in the noisy case, we can obtain upper and lower bounds by doing some more technical analysis. And these upper bounds and lower bounds can conclude that even in the phase noise case, when the number of stable phase block is larger, you can still obtain some appreciable advantage. Although when m goes to infinity, we know it has to go to the with the case without phase noise, because when m is large enough, you can establish a phase reference very precisely. And the takeaway message from this part is that the degradation from the absence of a phase reference is only log m over m bits per mode. And this would look like, it looks like that this degradation should be true for all kinds of capacities, even for the trade-off capacities. So I think this will also be true. This is true for quantum and the classical, and the Inhomogeneous quantum and entanglement-assisted classical case. And finally, it's the summary. So we derived the EA communication capacity formula for multiple access channels. We show the optimal encoding for the single standard case when noise is largest phase encoding on two-mode squeeze vacuum. And then we give some practical receivers, which in the end lead to experimental demonstrations. And we show that the rate region of thermal loss multiple access channel, there's a strict advantage. And when you have phase noise, we give some exact solution of the ideal case and bounds for the thermal noise case. And there were a lot of open questions, and we can discuss more later. Yeah, I will conclude now. And last, if there's any questions.
Many thanks. I have our standard two ones. So the first one is, what do you think will be the first use case for entanglement-assisted communication networks?
I think the first demonstration of advantage would be this classical communication, which we have already begun. But the first practically very meaningful use would still, I think, be still entanglement establishment, and using entanglement to do network protocols, or do network sensing protocols, or network computing protocols. That would be more useful in terms of applications.
Okay, thank you. What's the main hurdle?
Main hurdle is we don't have good quantum memory is one thing, and then how to establish entanglement, we have to have practical schemes. And I think one has to make use of the infinite dimensional hyperspace of bosonic modes instead of still using the just qubit-based protocols, and that will be able to actually give a much better rate, as we have already seen in this classical and quantum communication. Using the larger hyperspace of bosonic mode actually gives a benefit, and right now it's not being used.
Okay, thank you.